Okay, today we're going to be looking at something called impulse and collisions. So when we've been looking at collisions lately, and an area which we've not considered is what happens when two objects are actually in contact with each other. So if say we had our ball and a bat here, and the moment where the ball is in contact with the bat, what is actually happening? So the things that we need to consider when we're looking at the collision, we need to think of two factors. Firstly, the duration of the collision, and secondly, the magnitude of the force. So we're going to think about these two factors, and we're going to consider them firstly mathematically. So let's consider firstly Newton's second law. Force is equal to mass times acceleration. And we know that acceleration is the change in velocity over time. Now, if we combine these, so if we take F equals m, instead of A we'll put in v minus u over t, we then get F times t is equal to mass times the change in velocity. This can be thought as following: the force applied to an object for a multiplied certain time is equivalent to the mass multiplied by the change in velocity. This leads to the idea that the force multiplied by time is equal to the mass times the change in velocity. So we can rewrite this as F times the change in the duration of time where that the collision takes place is equal to mass times the change in velocity. The force multiplied by time it acts is therefore equal to the change in momentum. So this is the change in momentum. And we call this the impulse. So this whole concept is called the impulse of the collision. The impulse from one object is transferred to the other. It can also be explained by the conservation of momentum principle. When the two objects collide, momentum is always conserved, but the velocities of those two objects will be different from the before and after the collision. So when we consider the impulse, we're seeing that what we're seeing is that transfer of momentum from one object to another. So impulse is the change in momentum. Let's look at some examples to illustrate this. So a trolley of 4 kilograms is at rest and is acted on by 15 newtons for 3 seconds. Firstly, we want to calculate the change in momentum of the trolley. So we've got F times the time is equal to m times the change in velocity. So we've got 15 newtons and it's acted on the trolley for 3 seconds. The trolley has a mass of 4 kilograms and it starts at rest, and we want to find, we don't know how long, what then velocity is going to be. So we can calculate the change in momentum, which is the impulse. It's going to be 15 times 3 is our impulse, and that's 45, and it's Newton seconds is our units for impulse. And we can then use that to calculate the final velocity. So because it starts off at rest, the final velocity will be equal to the change in velocity, and we know that the mass times change in velocity is 45 Newton seconds, so the change in velocity will be 11.25 meters per second, and that is equal to the final velocity. Our second example, a golf ball is struck by a driver. Now, for anyone that doesn't know what a driver is a type of golf club. You get different types of golf club for different purposes in the game of golf, and a driver is the name given to one of them. The head of the driver has a mass of 0.5 kilograms. The ball has a mass of 0.045 kilograms. The club head strikes the ball and is in contact for 0.8 seconds, or milliseconds, sorry. So that's something to be paying attention to. It applies 2,500 newtons of force whilst it's in contact. At what velocity does the ball leave the club? So our impulse is force times time equal to mass times the change in velocity. The force is 2,500, and our change in time is 0.8 times 10 to the minus 3 because it's milliseconds. And we are going to be using the mass of the ball because we were concerned about the velocity of the ball, so we don't going to be using the mass of the club. So it's just the mass of the ball we need times the change in velocity. And remember, the velocity was 0 at the beginning. So we'll get the change in velocity is equal to 44 meters per second. So that's the velocity that it will leave the club. So another one, a car of mass 1,800 kilograms is travelling at 15 meters per second. In a test, it can stop within 12 seconds. What force must be applied? So in this case, the change in velocity is going to be minus 15 meters per second. because the car's decelerating. So the force times the time is equal to m times change of velocity. Now we know that it can take 12 seconds, and the mass of the car is 1800, and that's times minus 15. So this is going to give us a force of minus 2,250 newtons. Now, if we want to create a great impact or greater transfer of momentum, we'll need to have a large force, and it must be in contact for a larger time. So to create a great impact or greater transfer of momentum, we need a large force and long contact time. For example, in bobsleighing, to get the bobsleigh going and to maximise the transfer of momentum from the stationary bobsleigh to one that's hurtling down the side of the hill, the bobsleigh team need to be maximising the amount of time that they're pushing the bobsleigh, because that's the maximum time that they're transferring their momentum to it. However, in reality, most of these kind of problems actually will involve a short contact time. For example, if you think about in sport, when you're hitting a ball, or when two items collide, that collision time is going to be quite small. We've been considering the ideal. So if we think about the ideal of force over time, we've been assuming that force that we apply lasts for the time and then stops. This is what we call an ideal force time graph. But the reality is not like that. The reality would be more like this. So we've got our force and our time, and it's going to start at 0, and then it'll increase, and then and it's not going to be a nice straight line. It'll be all bumpy, and it'll have a shape, and that shape will depend on many factors. For example, the two mediums that are in contact with one another, for example. So the maths that we've been doing with our f dt is equal to m dv, this here is our ideal, and gives us an approximation. If we consider a hammer striking a nail, so let's consider what this would look like. So obviously, as you bring your hammer down, there's going to be a point where it just hits that nail for the first time. It's got 0 force, and it's suddenly going to go up, and it's going to go to, let's say it goes to 120 newtons in force, and then that's when it's its maximum. Then the hammer is drawn back, and then it'll go down again, and let's say it happens in 0.075 of a second. It's going to be a t. To work out the impulse, we've got f times the change in time. This is equal to the area under the force time graph. Now for more complex, if you were to you can see where this is going to lead you. If you look at these equations, this is going to lead us eventually into the realm of integration. But for this example here, we've got a nice triangle. So the area is equal to half 0.075 times the maximum height, which is 120, which gives us 4.5 Newton seconds. And then we could use that to, if we have the mass of the nail is 35 grams, remember it's grams not kilograms, we can work out the velocity that nail is going to go in. So we've got our impulse, which is 4.5, equal to the mass, which would be 0.035 kilograms, times the velocity, and the velocity of the nail is going to be 128 meters per second. Now in reality, that nail is not going to stay at a uniform 128 meters per second, because as it goes into the wood, there's going to be quite a large frictional force gripping onto that nail as it's driven into the wood. But at that moment of maximum impact, it's going in at 128 meters per second. Let us consider Newton's third law. So it states, if object A exerts a force on object B, then object B exerts an equal and opposite force on object A. This idea is mutual. This idea of mutual and equal opposite forces may be written mathematically as the force of object A, which we'll call F1, is going to be equal to the opposite force from object B, which we'll call F2. So let's put the impulse equations into this. So we've got so let's write our impulse equation as F equals the change in time is equal to mass times dv. So F is m dv over t. So we have m, which we'll call mass 1, the change in velocity of 1 over dt is equal to the minus of mass 2, I'll take that here, change in velocity 2 over the time. Now the times can cancel out, so we'll just have m1 v1 equal to m2 v2, that's going to be negative, and if we rearrange, we have equal to 0, which gives us the mathematical statement of the law of conservation of momentum. Let's look at one more example using this. So we're going to consider the International Space Station. And there's a supply craft and the space shuttle docking with the ISS. And they need to do that. This happens frequently so that crew and supplies can be transferred. The movement of the supply craft and the shuttles is controlled by small rocket thrusters positioned throughout the spacecraft, and this allows the craft to rotate and move away and so on. When the shuttle separated from the ISS, so they have to, the shuttle and the ISS have to connect together so that this transfer can happen, and then it has to separate off. When the shuttle separates from the International Space Station in order to return to Earth, it has to move a mass of 1 times 10 to the power 5 kilograms safely away. When leaving, the shuttle's rocket thrusters, fire, and a constant force of 2,750 newtons is applied to the shuttle. How long must the thrusters act in order for the shuttle to reach a velocity of 2 meters per second? So we've got our impulse. So the force from the thrusters is 2,750, and we want to find the time. The mass of the shuttle is 1 times 10 to the power 5, and we want it to reach 2 meters per second. So rearranging, we'll get a time of 73 seconds. So hope that helps.